Okay, so now we're starting chapter 2, which is looking at surface area and volume. And last day in class after your quiz, I had you do an activity where you looked at what a square centimeter looks like, again, to get an idea. And we learned that in a area measurement, such as 10 centimeters squared or 10 square centimeters, the 10 represents the how many. How many of those little shapes do I have? And the centimeter squared represents the of what. So this is a great way to think about things like that, because a square centimeter can be a what? It can be a little, that little square of edge length 1 centimeter each, just like a centimeter cubed is probably best thought of as a sugar cube. So what we want to be able to do today is basically work with these units. So here's a few questions. Get us used to how the numbers might change. Which area is bigger, 10 square inches or 10 square feet? Hopefully it's really obvious that feet are bigger than inches. Then we would think 1 square foot is going to be bigger than 1 square inch. If you think of a chessboard, now this isn't exact, but if you think of a chessboard, one of the little squares on the board, the red and the black squares, that you could think of that as 1 square inch, and you could think of the entire board as 1 square foot. So there's lots of those little squares on the whole board. Okay. So one of the things is if we have an idea, one of them is bigger, then the next logical question might be, well, by how much? So let's try to answer this. So we have an idea right now that a square foot is bigger than a square inch. We're going to compare these two things. Now when you're comparing things, we want to compare like units. Like units. We want to either change the inches to feet or the feet to inches. And in this question, I think it's better to change the feet to inches. If we change the inches to feet, we're going to end up with decimals, and that's not going to be very nice. So we're going to, when we compare things, we want to compare things that are the same. So let's look at our 10 square inch picture. Remember, one of the things we looked at in class was when you look at the what, you don't have to think in terms of a square as the area that occupies that amount. We can think about it as a rectangle. Rectangle's really nice. So in our picture right here, here's my 5 inches by 2 inches, and if we broke that up, there'd be 10 square inches in the middle. Okay. If we go with our feet, well, again, the rectangle is going to be way, way larger. So this is not to scale, but I'm just going to draw a little bit larger. And what we want to do is we want to figure out, well, in inches, what are the dimensions? And we know that 5 feet is equal to, well, 5 times 12 inches per foot, and we end up with 60 inches. And 2 feet is equal to 2 feet times 12 inches per foot, which is 24 inches. And in doing this, what we can then go ahead and do is to represent L as 60 inches and the width of my rectangle as 24 inches. And when we do our area calculation of a rectangle, which is L times W, we find out that the area of this rectangle is equal to L times W, and that ends up being 1,440 square inches. So obviously, 10 square feet is bigger than 10 square inches. And then the question is, well, how much bigger is it? It turns out to be 100. So 10 square feet is 144 times bigger than 10 square inches. Now, I'd like to ask you a question and think about it and bring it to class next day. Is there anything special about 144 in this question? So think about that. That's what we're going to start off with in class. 144, is that just a random number, or does that have more meaning? So again, a big idea, if you're comparing things, we want to make sure we compare um, the same unit. Now the one above is probably really obvious because I kept the how many the same. But maybe this question is not so obvious. Which one has a bigger volume? 1,000 cubic millimeters or 10 cubic centimeters? And again, it really doesn't matter what you imagine that volume shape to look like. It could actually be a cube, or it could be a rectangular prism, which just means, you know, a box, like a shoebox. So what I want to do is I always want to get in the habit of drawing a picture. So here's my millimeter one. And this one is, I can draw a nice cube if I actually wanted, because here's my dimensions. And given that 10 times 10 times 10 is 1,000, I can actually draw a cube. And we know the volume of this cube is equal to L times W times H, if that's the way you want to say it. So we might see the volume of a prism, rectangular prism, to be L times W times H. We also see the letter B, and what B represents is the area of the base. Either way, simple calculation. And in going ahead and doing this then, in this particular example, well, we know what it is. It's 10 times 10 times 10, which is 1,000 cubic millimeters. So again, I didn't want to go from millimeters to centimeters because I would have got a decimal. I could have, but I'm choosing to change the centimeters to millimeters. It would be really hard to draw a cube for 10, not a nice number. So I'm just going to draw a rectangular prism. Remember, a rectangular prism shoebox. So here's my quick little sketch. Sketch is always a good idea. I'm going to say that this is 1 centimeter, this is 5 centimeters, and this is 2 centimeters. But now what I want to do is I want to convert these to millimeters. And when we do that, I'm not going to do the calculation. You should be able to do that really quickly, easily. We end up with 10 millimeters, 10 millimeters in 1 centimeter, 50 millimeters in 5 centimeters, and 20 millimeters in 2 centimeters. And when we do our volume calculation here, we get 10 times 20 times 50, which is equal to 10,000 cubic millimeters. So in this question, the units are quite close, millimeters to centimeters. Is one bounce along our unit line. It really looks at this idea of, wow, we have 1,000 of those little cubic millimeters, and we only have 10 of these cubic centimeters. So there's a real disproportion in the how many. But as it turns out, the 10 cubic centimeters is 10 times bigger than the 1,000 cubic millimeters. So again, unit sense is really, really important. It's this idea of, well, what does 1 cubic centimeter look like? Well, that's a sugar cube. What does 1 cubic millimeter look like? Well, I don't know. That's really tiny, tiny. But at least I know it's really, really small. So the two questions on the previous page highlight some important ideas when we're thinking about and comparing measurements. First, we must have an idea of what the measurement unit looks like. That's just what I just talked about. I call this a unit sense. So what does a square centimeter or a cubic centimeter or a square foot or a cubic foot or whatever, what does it look like? Can you imagine something in your head? And unit sense is easier when you think of units of area and volume in terms of something that are not always squares and cubes. Again, it's much nicer to think in terms of rectangles and rectangular prisms, or, like I keep mentioning, shoeboxes. So let's work through 4 examples quickly in using this idea of units of area. Let's do some area calculations. First example, find the area of a rectangle with size 5 centimeters and 10 centimeters. Well, one of the first things we need to realize is what are the formulas we're using. We have a rectangle. Our formula is L times W. In this one right here, I want to know, I'm given my dimensions in centimeters and I want the answer in square meters. So again, what I'm always going to do is I'm always going to start off with a quick little sketch. And I'm going to label my dimensions. But again, we want our dimensions in, it would be better to have them in meter by meter, and when we multiply that with our unit analysis, we get square meters. So I need to change 5 centimeters into meters. And again, we've just done a unit on that, so I'm not going to spend any more time other than to say, here's what they are. And given we have these dimensions, area is equal to 0.05 centimeters, or sorry, 0.05 meters times 0.1 meter, which is equal to 0.005 square meters. And if we just did our quick calculation in centimeters, what we know is this equals 50 square centimeters. So again, there's this unit sense, how the numbers relate to the units. Okay, next one. Find the height of a triangle with an area of 56 square centimeters and a base of 4 meters. One of the first things I want you to notice is we have different units. We're given the area in square centimeters, and one of our dimensions is meters. We want to find the height of the triangle. So the first thing we really want to do is to convert 4 meters into the dimension we want, and we want centimeters. We could have also changed the centimeter squared to meters squared, but that would have ended up being a not nice decimal. So we want to try to help ourselves as much as possible. It's always a good idea to draw my picture. So here's my shape, here's my base, and what I want to know is, what is that right there? I want to know, what is the height? Again, the formula for a triangle is 1/2 base times height. And this is the moment I say, well, now, in order to finish this question, it's Fisher-Price math. You put the right thing in the right spot, and then it's just a matter of doing the calculation. So the right thing in the right spot in this question becomes, well, area is 56, 1/2 is set, my base is 400, and I want to know my height. And now I just go ahead and I solve this equation, collect those terms, isolate the h, remember we want to figure out the height, we undo a multiplication with a division. And when we do this on our calculator, the height is equal to 0.28 centimeters. And again, that number should make sense. You got a really wide, not centimeters, you got a really wide triangle. You're not going to have a very high one. Okay, last two. Find the side length of a cube if the volume is 0.125. Now we know the cube formula. It's equal to side times side times side, or s cubed. Now, to ask you a question about a cube, really the numbers have to work out. And we know the, again, Fisher-Price math time, you put the right thing in the right spot, and then you go ahead and answer the question. One of the key things we need to notice is I want to know how long the side is in centimeters, but my units are in cubic meters. So again, different ways you could go about it. You could convert cubic meters to cubic centimeters and then find out, or you can answer the question, how long is the side in meters, and then convert. What I'm going to do is I'm going to do the latter. I'm going to treat it as meters cubed. I'm going to figure out what the dimension is in meters, and then I'm going to convert that to centimeters. 0.125 is equal to side cubed. Algebraically, in order to undo a cube, I need to take a cubed root. So if I have something cubed, the way we undo a cube is we undo a cube with a cubed root, just like we undo a square with a square root, and so on. So what I need to do is undo a cube with a cubed root. I need to follow the golden rule. What I do to one side, I do to the other side. And when I do that, I get S is equal to, well, the cubed root of 0.125 is actually a nice number. It's just 0.5. Remember, our units are meters because we are playing with meters cubed. Finally, what I need to do is figure out that the side length in centimeters is 50. Again, if you're interested, do it the other way. Convert 0.125 meters cubed to centimeters cubed, and then you're just going to have to take the cube root of that number, and it'll be 50. Okay, last one. Find the area of a right triangle that has a hypotenuse of 13 centimeters and one leg of 5 centimeters. And again, a great idea is to draw a picture. So if I draw a picture of this triangle, again, it says hypotenuse, so I'm hoping you automatically know if it has a hypotenuse, it has to be a right triangle. The hypotenuse is the longest side. It is the side opposite the 90-degree angle. And the other two sides don't really matter. They're just legs. They don't have a special name. So I want to find the area of this right triangle. The formula for the area of the right triangle is, well, 1/2 base times height. We have the height. We have the half. I want to know area. The problem right now is I don't have the base. I need to determine the base. In order to determine the base, we're going to have to use something else that you've been doing for a while now. We're going to have to use Pythagoras. Use Pythagorean theorem to find the other dimension of our rectangle. I'm going to call that b then, b for base. And if you remember, Pythagoras is a squared plus b squared is equal to c squared. And this only works with the right triangle. Again, that's a little formula. Right now, it becomes Fisher-Price math time. 5 squared plus b squared is equal to 13 squared. 25 plus b squared is equal to 169. Again, I'm solving an equation. I want to isolate b, bring the 25 over by subtracting it from both sides, and then I undo a square with a square root. And what I do to one side, I do the other side, and I end up with my base is 12. So I do a lot of extra work here in order to find this number. When we go ahead and plug that number into the formula, we get 30 centimeters squared. So again, beware of your units. So what are our key ideas from today? Key ideas are unit sense. What does something look like? Again, that's going to help you with, does my answer make sense? I might have made some algebra errors, and unit sense will hopefully go, hey, that can't be right. Drawing a picture, super important. Simple pictures, but super important. Not only drawing a picture, but labeling. I think that has one L, might have two. The other thing is, well, just solving whatever you're asked to do. And I'm going to call that algebraic manipulation. Algebraic manipulation. And the other thing that we have to carry forward from last unit are, hey, you need your conversion factors. That's on your blue sheet.